Okay, so we know our CPU is nothing but ALU, registers and control unit, right? Registers, ALU, if you have any memory unit, they are connected via common bus. The control unit is now responsible for generating the control signals to these all parts of your CPU so that it can complete an instruction execution. So finally, the processor is meant for executing an instruction. Okay. So to perform the execution of your instruction, the sequence of actions have to be done. Okay, with respect to time, with respect to clock pulses, the control unit will generate the required control signals in a sequential manner. Okay, so such control unit now can be implemented in two ways. One is hardwired control, another is microprogrammed control. The name it says hardwired control unit means we use hardware components like logic gates or flip-flops or multiplexers or adders for implementing the control unit. The other microprogrammed control, we will use a program, nothing but we will write another instructions for generating the control. Okay, so it's a kind of a program written in a control memory that is responsible for generating a respective control signals. Okay, so let us see the basic differences. First of all, hardwired organization. So here in this, the control logic is implemented with the help of gates, flip-flops, decoders, and other digital circuits. So with the help of hardware components, we will construct the control unit, which is responsible for generating the control signals. Okay, so here the control signals are the inputs that are needed for multiplexer for selecting one of the register or the memory, which places the data on to the common bus, or the controls for the registers like load, clear, and increment, or the controls for your add and logic unit ALU to declare the operation to be performed on the accumulator along with the data register, or just the accumulator. Okay, so these control signals will be generated by using a control unit. In hardwired organization, we use hardware components. So as and whenever any module, if you develop with the help of hardware, the basic advantage is fast mode of operation. Hardware implementation gives speed. Okay, so it has the advantage that it can be optimized to produce fast mode of operations. Next, coming to a disadvantage, I can say, so in a hardware control, it requires changes in the wiring among various components if the design has to be modified or changed. Okay, if you want to modify change any updations, if you want to do, or if you want to add one more extra instruction in your ALU, then the respective control signal have to be updated. See, for example, my ALU initially, I have assumed that it can perform 8 operations. So my control sequence will select 1 out of 8 operations by using the 3 signals, 3 control inputs. So 3 to 8 decoder I will use to select one particular operation. Later on, I want to upgrade my system, which will add 2 more instructions, let us suppose, so that my instruction set is increased to 10. To implement this 10 different control signals, I require to change my decoder to 4 to 16, because minimum 4 selections I require, right? So you have to replace the hardware components, or else you need to adjust the wiring among the units. So the design has to be modified or changed. Okay, so that's what the difficulty, I can say the disadvantage in hardwired control. But the other end, it is fast when compared to the other organization, which is microprogrammed. Okay, next, coming to microprogrammed organization. So here the control information is stored in a memory. We call that memory as control memory, and the control memory is programmed to initiate the required sequence of micro operations. Okay, so this will initiate the required sequence of micro operations by which the CPU can perform its operations, right? So I can say one of the example, like OS initialization programs, whatever we have. So at the time of initialization of your computer, right, start of computer, some control memory, some in that control memory, some program has to be run before startup work with your front end. Before opening your Windows tool, something has to be gone at the back end, right? So that I can say this as a control program, which is protected version. Okay, so helps for initialization of the system. That's one example for microprogrammed organization. So in this microprogrammed control, any required changes or modifications, if you want to do, it is, since it is a program, you can simply change the program. Okay, so from updating the microprogram in the control memory is sufficient for doing any changes. Okay, so rather than changes in the hardware or the wiring or the components, it is easy for updation of the program in microprogrammed organization. So this is the basic difference between hardwired and microprogrammed organization. So which is very, very important. I mean, widely frequently asked questions, this one. So let us see now the hardwired implementation of your basic computer control unit. This is example for hardwired implementation. So so we know we are now generating control signals for execution of an instruction, right? So we have several stages in your instruction execution. So first thing, we will be having our instruction code in instruction register, right? So this is IR, instruction register, which is having our 16-bit instruction code. And this control unit in this figure, if you observe, it is having a decoder a decoder which is of 3 to 8 decoder, and one more decoder 4 to 16 decoder, and another sequence counter, which is a 4-bit sequence counter, and then the control logic gates. A number of control logic gates are there. Okay, so this implementation right now we are not viewing. So anyway, this 16-bit information available in the instruction register is decoded based on the type of instruction, right? We know, see here, these 3 bits, 12, 13, 14 bits are given to a decoder so that I have a possible opcodes vary from 0 to 7, right? So if these 3 bits are 1, it refers to either register or IO reference instruction. Other than that, other than 7, any of the opcode 0 to 6, this relates to memory reference instruction, and 0 to 11, these 12 bits giving the memory address, and the most significant bit I under a memory reference, this specifies whether it is direct or indirect. Under if my 7 is the decoder output, then this specifies whether it is register reference or IO reference. Okay, so these are the inputs given for your control logic gate, right? And along with this, we'll be having a clock, a system clock, so by which it will generate a clock pulses or the timing sequences. Each clock pulse is called as one time state, one timing sequence, T0. Likewise, I have a 4 to 16 decoder so that I can have up to T0 to T15, 16 time state. Okay, so why just 16 means, see, for your instruction execution has to be finished by using any number of these timing sequences, time states starting from T0. It can end in with any other time state at any other time state, probably only T4, maximum 4 time states it will take for completion of instruction. For delayed instructions, it may extend. Okay, so for that it facilitates 16 time states, and these time states and this input is given for control logic gates to generate the required control inputs. Okay, so this is a simple control unit which is implemented, organized in hardwired in a basic computer. So let us see what is this timing or the time states. So this is what that figure just explains. The instruction register is divided into, of course, 3 parts: I bit, opcode, and 12 bits that refers to memory or register operation based on the operation code. So the operation code in bits 12 to 14 are decoded with the help of 3 to 8 decoder. The 8 outputs of decoder are designated by D0 to D7, and the subscripted decimal number is equivalent to the binary, of course, D0 to D7, and bit 15 refers to the direct or indirect during memory reference. During if the output of the decoder is D7, then this I bit corresponds to distinguish between register reference or IO reference instruction. And the 4-bit sequence counter can count in binary from 0 to 15. The outputs of the counter are decoded into 16 timing signals, which are termed as T0 to T15. So the timing signals, whatever is the counter, sequence counter, it is initially cleared. The counter is initially cleared to 0, and it will increment, or it can be cleared synchronously, right? The while it increments one by one, the timing sequences, it generates the timing signals T0, T1, T2, T3, and so on, right, up to T15. After T15, again the sequence counter cleared. But at any time instance, at any stage, if you want to start the counter again from T0, then I can use the control input clear, by which the sequence counter again can be cleared. Okay, so which we have here clear. So after 4 time states, if your instruction is finished, again you have to start from T0. So I can apply this clear input so that it restart from generating the timing sequence from T0. Okay, so that is clear input which helps to restart the operation. See, this is how the timing signals are coming. So this is your clock on every rising edge. So I for every the gap between rising to rising, this is treated as one clock pulse. One clock pulse is considered as one time state. So this is your T0. During T0, the T0 output is like this. This is 1, and remaining all states T0 is 0. And for the next clock pulse, T1 timing starts. Next clock pulse is said to be T2, T4, T3, T4, T5, likewise, and so on. Okay. See, for example, after T4, if your operation is finished, let us suppose, then if you want to restart it from again from T0, then you have to clear the sequence counter, right? So to clear the sequence counter, I have to apply the bit clear sequence counter control, right? CLR clear. So when this has to be cleared, of course, if my condition is during D3 and T4 time, if your decoder output is D3 and at the time instant T4, right? If you have a decoder output D3 as 1 during whenever these two are 1, then in that time I want to clear the control sequence counter, I can give this clear input as 1. Okay, so with this, the sequence counter again it is clear to 0, right? So SC is 0, so the next clock pulse is set to be T0. Next clock pulse is T0, next clock pulse T1, T2, and so on. Okay, likewise, still it will generate T15. At any state, you can clear the sequence counter so that it again reinitialize from T0, T1, T2, T3. Okay. See, what is the need of these timing sequences? Let us see with the help of the instruction cycle. So in a basic computer, we know our set of instructions will be written in a program memory as per the stored program organization, right? So initially you have your program in your memory and that has to be executed by your computer. So we will mention what is the starting or the first instruction address. So how we mention that? So first instruction address is copied into initially your PC. Program counter will hold the first instruction address of the first instruction. So as and when you have a PC loaded with your first instruction address, then your computer has to fetch the instruction from your memory, right? Reading the instruction from your memory and loads it into the instruction register, right? After that, the decoding circuitry will decode the instruction. Okay. So decode the instruction by whatever in the previous diagram we have seen few decoders which decodes the bits. What is the first bit, what are the next bits and subsequent bits, by which it decode, the decoder circuitry will decode those bits, and it came to know the corresponding operation and operands addresses and all, right? So after decoding, if your second operand, if you want to perform an operation between the two, then you require the second operand. For example, if it is memory reference, okay, so you have to read the memory for your second operand. Okay, right? So what is the address of the second operand? It is available in the remaining 12 bits. Whether those 12 bits are the direct address or indirect address, again, the most significant bit will specify. Okay. So if it is not the direct address, then I have to calculate what is actual address. We call that as effective address. Okay. And then you need to refer the memory, read the memory for your operand. Okay. So memory read you need to do. After that, by using ALU, we will execute the instruction. These are the steps that has to be done for memory reference instruction. For, of course, for a register reference, let us suppose if it is register reference, fetch is common, decode is common, right? Reading a memory will not be happened. Of course, accumulator itself holds the instruction. So reading memory will not happen, but the execution will happen. Okay, right? This is register reference. If you come for IO reference, fetch is same, decode is same. Next, third thing, execution is nothing but loading the contents of input onto the accumulator. Okay, right? If it is output type of instruction, then copying the contents of accumulator onto the output device, right? So either thing has to be happened. Okay, right? So earlier it may take 4 steps, either in register reference or IO reference, it will take just 3 steps. Okay, so these steps have to be completed for every instruction. Upon completion of step 4 for the first instruction, the control has to go back to step 1 to do the fetch, decode, read, and execute of the next instruction, which has to be repeated continuously until the end of the program, or else until you mention any halt instruction which causes stop of your program execution. Okay, so these steps have to be repeated continuously. Okay, so to repeat these actions, we use now the timing sequence, and in every stage the corresponding controls have to be activated. Okay, so that is explained with, and these cycle of operations, whatever we have, step 1, step 2, step 3, step 4, this is repeated continuously. So hence we call this as a cycle, and it is meant for execution of an instruction. So hence we call it as instruction cycle. Okay, so instruction cycle indicates or includes several stages which are called fetch, decode, memory read, or execute. So memory read is an optional one, right? So for memory reference, this stage will come into picture. For other type of instructions like register or IO reference, the third step will not be there. Okay, so execution is nothing but copying the contents of accumulator from or to input or output devices. Okay, so during register reference, you may increment the accumulator contents, or you may shift the accumulator contents, or you may do like clearing the accumulator contents. Anything that can be said to be an execution. Okay, so right, these steps are repeated continuously for every instruction in your program until the completion of your program, right? So it's a cycle of operations, has to be repeated continuously. Okay, so let us start with the first stage, how the timing sequences and the control inputs are generated. So first stage is fetch. So fetch is nothing but we have address of instruction in your PC, right? So PC, program counter, holds the first instruction address. Okay, so what you have to do, see, from your common bus system, if you observe, see, the contents of PC are not directly connected to the memory unit, if you observe, right? Okay, only contents of AR, address register, or AR is connected to the memory unit, but not the PC. Okay, so to read an instruction or to read a 16-bit information from your memory unit, whatever it is either instruction or it is a data, via AR only you can read. So AR holds the address of the data, address of the word available in your memory unit can be read. Okay, so AR should hold what is the address reference, memory reference address should be held in AR. Okay, so the first step for fetch instruction is nothing but getting the 16-bit information which regarding instruction code into IR. Instruction register should hold those 16-bit instruction code. That is what fetch, right? So to do so, we know PC holds the 12-bit first instruction address, right? That has to be first copied onto AR. Okay, so AR need to be copied with the contents of PC. How can you do this? Okay. How can you copy the contents of PC onto AR? So to copy contents of PC into AR, we need the common bus, right? So initially, with the help of common bus, I will select the PC by using 0, 1, 0 selected lines, so that PC is selected for placing the 12-bit contents onto the common bus. After that, the load control signal of AR is activated, so that the contents available, 12-bit contents available on the common bus are copied, loaded onto the register, address register. Okay, so to do so, I require a common bus system. Okay, so this is happened in first timing sequence during T0 state. Okay, so during T0 state, right? So address contents of PC are copied into AR. Right? So this should happen in initial T0 state. Okay. Right? So whenever you require access of the common bus, right, which is a resource of your CPU, apart, it requires one timing sequence indirectly. Okay. So during one time sequence T0, we are doing first transfer between the two registers, PC and AR. Now, from AR, whatever is their contents of AR, they are connected to the memory via these lines. Okay, right? So the contents at this location, that will be placed into IR register. Instruction register should hold the contents of this location, right? So how can that happen? We have address of memory to be read in AR register, so that is connected to the memory unit via address lines, right? So via these parallel address lines, the memory location is selected, and that corresponding 16-bit information is placed onto the common bus. It has to be placed onto the common bus, right? So for placing this onto the common bus, you have to select the memory. So 111 select lines have to be done. So this 16-bit information is now placed onto the common bus, and this 16-bit information need to be accepted by the IR register. So you have to activate the load control signal of IR, so that 16-bit register code will be copied onto IR. So that is done in T1 next time instant, because we require again the common bus for transferring the data. Okay, transferring the information. IR is loaded with not the contents of AR, but the contents available in the memory whose address is in IR. Okay, so hence I have written like this: memory contents of address available in IR. Okay, right? So this is after this we have finished fetch operation, right? So this is what called a fetch operation. Okay, fetching is nothing but reading an instruction code and places into an instruction register. So with this one fetch operation is finished. So at the time of fetch itself, one more micro operation is finished. Okay, that is what? Incrementing the contents of PC by 1. Okay, so during T1 itself, during fetch itself, the contents of PC are incremented by 1. This is very important action that is done, because for incrementing the contents of PC, you just need to activate the increment control of PC. You don't require the common bus. So hence, these two can be completed in a single time sequence, which is T1. Okay. So to perform any operation, if you don't require the other resource which is used by other micro operation, then I can implement the both in parallel. Okay. So PC is incremented by 1 here itself to point to the next instruction to be fetched. Right? I think I'm clear. See, this concept is very, very important for every processor, whether you are dealing with a microprocessor or a microcontroller or a ARM processor or a DSP processor. So the basic instruction execution is only the 3 stages. So how the things are happened in your inside the computer is clear only if you understand this concept, right? So T0, it places the contents of PC onto the bus by making the bus selection inputs initially as 0, 1, 0. Okay. So after that, it transfers those contents accepted by AR by enabling the load control input of AR. Okay. See, this is what the control unit that is happened. Okay. So for explain it simply, first what is doing in the timing sequence T0 that you can observe here. See, with T0, so what you have to select initially at T0, you have to select the bus S2, S1, S0 as 0, 1, 0, right? So during T0, this will be S1 will be 1. Am I right? S2 and
Yes,
S0 are zeros. So none of the lines coming from T0 are connected here. Okay, so they are zeros right now. So this will select PC. Okay, so this will select PC. So since this is 2, it will select PC. So this places the contents of it here, right? So after that, I will activate the load control signal, right? Load control signal of IR. When you have to activate load control signal of IR, so that will accept the data available on the common bus during, sorry, not IR, AR, right? Address register, AR. Sorry. The PC contents have to be transferred to address register. That is the first operation. Okay. So address register has to accept this 12-bit information available onto the common bus, so that the load control of AR have to be activated. When this has to be done, so the activating load control of AR should be done during T0 time. So this T0 itself is connected to load control signal. So this is your T0 and that is connected to your load control signal. Okay, so this is first micro operation, which is contents of PC are transferred to AR. So which is done by this diagram. Okay, next, the address which is available in AR, that is connected to memory via these lines, right? And this places, now memory unit will place the 16-bit instruction code onto the common bus after selecting the memory, right? Okay, so you have to read your 16-bit information from memory and places into IR register. That is the next next micro operation. Okay, so memory unit will place its 16-bit instruction code onto the common bus. To place that data, you have to select the memory unit. So S2, S1 should, S0, they all should be 1. Okay, so if all these should be 1 in which time interval? T1 interval. So I have one more time interval, which is T1. So T1 has to be connected to S2, S1 and S0 also. But S1 is already connected to T0. So either T0 or in T1, in both the cases, S1 should be 1. So that I am using 1 OR gate here. So I'm using one OR gate here. One is the input, it can come from T0, or the second input of this OR gate can also come from T1. Either of the two time states, S1 will be 1, right? Okay, so at this instant, now your memory will be selected, which is now responsible for placing 16-bit information onto the common bus. Okay, and this 16-bit information is accepted, has to be accepted by your IR instruction register, because the 16 bits are belonging to the instruction code. So now the load control signal of this IR have to be activated. So during which time interval? T1 sequence, right? So T1, at T1 time, the load control of this has to be connected. Okay. And at the same time, we are incrementing the contents of PC by 1 to point to the next instruction, because this doesn't require the common bus. So I can do the same operation in the same interval, which is connected to increment control. The same time sequence is connected to increment control pin of your PC, INR. Okay, so the same T1 is connected to increment time pin, control pin. So as and when the address is available, this memory unit won't places the data onto the common bus unless it has the control signal. That's what called memory read control, which has to be done in T1 instant. So the same T1 is connected to this unit. Okay. So the combinedly, these two micro operations T0 and T1, it looks like this. So it has here facilitated with some n input OR gate, because for the next time sequence T2, few more inputs may come into picture, which will activate some other register, right? Likewise, for facilitating, for adding other states, we have given multiple OR gates. Is this clear? Register transfer for fetch phase mainly.
Yes, ma'am.
So likewise, this is for fetch. And next, coming to the decoder. So coming to the decode unit, right? So the decode, how the decoder, we have a 3 to 8 decoder. Whatever are the 16-bit inputs available in IR at this instant now, right? So the 12, 13, 14 bits of IR, 12, 13, 14 bits of IR are given to the decoder, which produces the outputs from D0 to D7. And the 12-bit information, which is available in IR, least significant 12 bits, are copied onto AR, and then I flip-flop is stored with instruction register, most significant bit. Okay. Okay, so this is what happening in T3. Sorry, in T2, this is what happening, because why I require T2? Because decoder, it will do its own. Copying most significant bit of IR into I bit, it will do it by its own. But the 12-bit information, least significant 12-bit information in IR will hold available in copies in AR. For this, you require common bus. So one time sequence you require, that is in T2 it will do. Okay. So in T2, if you add this, you require one more time sequence. So which is T2. If I add that also, so T2, it has to first select IR, right? So IR will places the least significant 12 bits onto the common bus. Okay, so to select IR, it should be 101. Okay, so T2 is connected to S2 and S0, but not for S1. So this will select IR, it places the not just 12 bits, it places all the 16 bits. Okay, because IR is 16-bit data, so it places that 16-bit information onto the common bus, and that will be accepted by your AR address register for after activating the load control signal. So this LD is now connected by your T2. One of the input of LD is connected by your T2. Since AR is just 12 bits, so least significant 12 bits available in the common bus out of 16 are just accepted by AR. So this is done in T2. And remaining bits are decoded by using the decoder and the flip-flop, right? So now during T3, reading of your memory will happen if it is memory reference instruction, which is done by detecting what is the decoder output, whether the decoder output is D7 or not. Okay, if it is D7, then it proceed for the other actions like register reference or IO reference. If it is not D7, then it will go by memory reference type, which will read the memory unit for data item, right? Okay, so during T3, memory read can happen if it is memory reference. If it is IO reference or register reference during T3, execution of the instruction will happen. Okay, so that is explained in the next slides. So T3, the timing signal is active for the decoding T3. During T3, the control unit determines the type of instruction that was just read from memory. Okay. See a combined diagram. See here D7, I bit and T3 bit. See, all are ones. What happened? See, D7 is 1. Observe the values. D7 is 1, I bit is 1, T3 time is 1. When all are 1, it refers to an indirect memory instruction. Am I right? I is 1 means D7 is 1. It means sorry. D7 dash should be there. D7 is equal to 0. D7 dash should be there. D7 is 1 means it is register or IO reference. Okay. D7 dash is there here. My mistake. D7 dash. Okay. See, the same we have explained with the help of whatever we have explained till now, that is represented with the help of flow chart. So initially the sequence counter is 0. So this starts generating the timing sequences from T0, T0, T1, T2 and so on. So during T1 initially fetch has to be happened. So T0 and T1 are required for fetch operation. PC contents are copied onto AR. After that, memory read happened for loading the instruction code into IR register. At the same interval of time, PC incremented to point to the next instruction. This is fetch. And T2 stage is your decode. This is what this complete portion is your decode. Decoding the type of instruction. Okay. So decode operation is IR 12 to 14 bits are given to the decoder, and AR holds the IR least significant 12 bits, and I flip-flop holds the most significant bit. Now the decoder output is checked. If the D7 is 1, if the decoder output is 1, it means opcode bits 12, 13, 4, 14 are all ones. If it is all ones, we know the instruction is either IO reference or register reference. If it is not all ones, okay, if it is not all ones, it means it is corresponded to memory reference instruction. So D7 dash is the path for memory reference instruction. So once you have D7 dash, after that, dash is nothing but complement. After that, we are checking for I bit, the most significant bit. This will specify whether the given 12 bits are memory direct address or indirect address. Okay. So if I is equal to 0, it means it is direct address. Okay. So it is direct address. We will be having the data during T3 interval, whatever is the address available, so that will be the 16 bits are copied into the memory of AR. This has to be happened. So the data item is available in DR register, memory read. Okay, after that execution will be happened. If I is equal to 1, it means the 12 bits are not the direct address. Okay, so they have it has another memory address where you have your actual data item. Okay, so one more memory reference, extra memory reference you have to do for getting the actual address of the operand. After that, the execution is done. Okay, so this is other memory reference type. So D7-I, this is I, this path is capital I, and in T3 state, you need to perform this action. Okay, one memory reference, memory access has to be happened for your actual operand. If D7-I-, okay, D7-I-T3, D7-I-T3, you no need to do anything except reading the memory for your operand. Okay, so only one memory access is sufficient for accepting your data. Here, after address, one more memory access you should do before the execution. Okay, so that is the difference between I equal to 1 and I equal to 0. This is a memory reference. Coming to the register reference, where this path is just for D7. True logic D7. D7, if I is equal to 1, then it is IO instruction. So D7, I, this path is for I. D7, I and T3. D7, I, T3 is meant for executing in IO instruction. This path, if you see D7, I-T3 is meant for executing register reference. D7, I-T3 for executing register reference. Okay. So this completes your instruction. After completion of the execution of the instruction, either it may be memory reference or IO reference or register reference. So since the completed, it completed one instruction execution, then it has to start fetching the next instruction. Okay, so to proceed, it need again the same timing sequences T0, T1, T2. So for that, you will clear the sequence counter by 0. Okay, so during the same T3 interval, we also activate the clear input of your sequence counter to 0. So this starts again from T0 state, and it proceeds for the instruction, next instruction, fetch, decode, and execute, and all. Okay, so this is the complete instruction cycle execution. So these are the list of execution of register reference and memory reference instructions. See, till T3 we have seen. After that, what is happening under memory reference, under IO reference, and our register reference, that we will see next class. Okay, so till now we have seen up to T3. After T3, how the instructions are executed. Okay, so based on the type of instructions, maybe clear accumulator, clear the E bit, complement accumulator, complement E bit, how it has happened, those were explained here based on the opcode. Okay, so because IR, those 3 bits, the 12 bits IR bits will specify the operation, right? So you have to extract which bit is responsible. Based on that, the opcode is decided. So you have to now decode the 12 bits for executing the register reference. Similarly, IO reference and memory reference. Memory reference anyway simple. The decoder outputs, based on the decoder outputs D0 to D6, we have what type of operation you have to do. Okay. So this we will see in next class. Is this clear? Do you have any doubts in the instruction cycle?
No, ma'am.
Okay. So please, these concepts are very important. Instruction cycle. Later on, we'll be having one more cycle called interrupt cycle. You know, while doing your computer, this sequential execution, if something interrupted, okay, it has to stop the execution and proceed execution of that program and then come back, right? Okay, so how it has been implemented, that is also very important. Interrupt cycle, one more cycle. Okay. So please, if you have any doubts, please ask me. Refer Morris Mano for the information. Let me collect the attendance. Don't have pen.